Now I want to continue with defining a group. So this is 1.2, definition of a group. So I want to write a definition here, and after that we just consider our main example. First example, which will be this group of symmetries of a triangle. So we take a regular triangle which has vertices A, B, C, and let me just draw the symmetries. 1, 2, 3. This will be called SB, SC, SA. And then there is this rotation, which I will denote by R, which is this rotation by 2 pi over 3. And then there is this rotation by 4 pi over 3. Finally, there is this identity which just does nothing. So these are symmetries of a triangle. And so the symmetries form a group. So what is a group? Let me finally give you the definition. So a group G is a set which will be also denoted by G, and this is a set of symmetries of something, if you wish, with an operation. And operation means a map from G times G to G. So it's called composition sometimes, sometimes multiplication, and the word operation means nothing. It just means it's from G times G to G. So it takes a pair G1, G2 and associates to an element which we denote by G1 times G2, and you can omit the dot as usual. So we will discuss the notation for it and so on in the next section. So this map should satisfy certain properties. And there are three axioms, 3 properties of a group. And these 3 properties are kind of obvious if you think of a group as a group of symmetries of something. But if you just say it's a set with an operation, you need to postulate them. So the first one is as follows. It's called associativity, and it says that for every 3 elements G1, G2, G3 in the group, we have G1 times G2 equals to G3. And, G1 times G2 times G3 equals to G1 times G2, G3. So it's true for any 3 maps. If you have a composition of 3 maps from one set to second to third, and you have a composition, then, 1, 2, 3, G1, G2, G3, then it's always true for any 3 maps. And here, so it will be true, for instance, for symmetries of a triangle, or because after all, the symmetries are just isometries, maps from plane to its self-preserving distances. And what it means that we expect it from anything, which is a set of symmetries of an object. But if you just say this is a group G plus this map, you need to impose it, because some maps like that absolutely don't satisfy it. So the second one is that there exists a special element denoted by E inside a group such that G times E equals E times G equals G for every G in the group. So this element corresponds to the symmetry which does nothing. If you do nothing and then do any symmetry, or do any symmetry and then do nothing, you will still get the same symmetry. So it seems like not a very strong property. The first one is very strong. The last one is also very strong, and it says that for every element G in G, there exists an element which I will denote G prime, meaning just another element in G, but usual notation is G inverse, like power minus 1, such that G prime equal G prime G is the identity. So where this one comes from? I mean symmetries has this property that they preserve something, and they are usually bijective maps. So what it means you can reverse a symmetry. You should be able to kind of do it backwards. And this G prime is exactly doing the symmetry backwards. Okay, so these are three axioms. Every set with a map like that satisfying these three axioms is called a group. And in this course we will study these sets, we will study these groups, we will classify some of them. For instance, if the order of G's number of elements in the set is prime numbers, there is only one such group, miraculously. So we will study them. And you can think of each such G as a symmetry pattern of objects in the outer world. Okay, so let's look at this group, this G, in particular, from the point of view of these axioms. So firstly, there are 6 elements here, and it's E, R. So then it's easy to see that this one is just R squared. So if you do this rotation by 2 pi over 3 twice, you will rotate by 4 pi over 3. So this element is just R squared. R squared means R times R. And then there are 3 other symmetries, SA, SB, SC. That's it. So first idea is that if we compose any elements here, we get again elements from this list. And that's not absolutely obvious. So for instance, you can do something like compose R with SA. What will you get? And that's an interesting question. So let me maybe compose SA with SB to just see how it goes. So how to understand what this symmetry is? So for this it helps to think what it does to vertices of a triangle, because it's easy to see that any transformation, sending plane to plane, preserving distances, sending triangle to itself, it will map 3 vertices to the same 3 vertices, maybe in different order. So let's see what SA composed with SB does to A, B, and C. So if you look at A, when we think of this SA and SB as maps, so it means we first do SB, then SA as usual, kind of think of it as a map. So point A under SB goes to C, under SA, C goes to B. So A goes to B eventually. B goes to under SB, it stays. Under SA, it maps to C. Finally, C clearly has to go to A, but we can see it because under SB it goes to A. Under SA it stays, so it's A. And A, B, C going to B, C, A goes to B, B goes to C, C goes to A. It is a rotation. So it may be not like formal proofs that this is exactly R. We will prove such stuff later on when we discuss isometries and when we discuss actually geometry of plane transformation, but you see that. And maybe a little exercise is that SB times SA, so basically the same 2 transformations in different order, give you R squared. So it means that multiplication in a group, you cannot change simply the order of 2 elements in general, for instance in this group. Sometimes you can, we will discuss it, but in general you cannot. So it matters. And now you see that we have a very rich structure here. You can multiply SA with SC, R with SA, and you always get an element from the same list. So it's pretty interesting already, I guess. Finally, let me discuss, so this identity element is here, so it clearly satisfies the second axiom. Let's look at the third one. So we need to find inverse to every transformation. So let me just list them. So E inverse is of course just E. If you multiply identity with identity, you get identity. Just because you do nothing, still do nothing. Happens to all of us. So this is why that's obvious. So then if you do SA inverse, you want some transformation which composed with SA will kind of return back. So SA is a symmetry, and if you want to return back, it's the same symmetry again. So that's why SA inverse is SA. Also, you can think that SA squared is identity, which is also true. Similarly, SB inverse is SB, SC inverse is SC. Finally, R inverse. So R is rotation by 2 pi over 3, and you want to do it backwards. We don't have a backwards rotation exactly, but if you just look at what happens to points, rotating by 2 pi over 3 backwards is the same as rotating by 4 pi over 3 forward. So that's why R inverse is R squared. And similarly, R squared inverse is R. And so you see that we have like perfect picture where for every element we have the inverse one. For some elements it's just the same element. For this 4, for this 2, it's not the same element. So that's an example of a very rigid group. This group has a name. We will call it later S3. It's a symmetric group of order 6. And we will study this in great detail. Okay, so what's the next plan? So in the next section, I want to discuss more in more detail certain properties of groups in general, and maybe go into some more detail of how to operate with these axioms. So then we look at interesting examples, in particular related to this generalization of this S3 group.